So my work is again on the implementation. Can you hear me? Okay. So my work is on the implementation side of things, and in particular Haskell. So imagine a world where you're using Haskell and you don't have to, so you want to use profiling for your program. So the case at the moment is you want to use profiling for your program, and now you have to recompile all your libraries because you forgot to compile your libraries in profiling mode. Or say at the moment, if you're downloading a package from Haskell, from Hackage, you have to compile it on your machine. Imagine you could just download a binary, and no matter which platform you're on or which hardware platform you're on, you could just run it and use it locally, or ignoring C libraries. And another common problem that many in this audience, I think, have, at least anyone who's trying to write high-performance libraries for Haskell, is that you have GHC and you have your high-level program, and then you send it to GHC, and then GHC does some inlining and these fusion rules fire, and the program gets rewritten, but not quite. So you end up with a program that is a little bit faster than like the Leaf program, but nowhere near close to where you would like it to be, to like beat C or Fortran. So the problem is that GHC is a static compile. Okay, let's go to the next one. Maybe the last point. So say you have a program that's running, and you would like to know where it's spending its time. And normally you would have to stop the program, recompile in profiling mode, run it. But if you have a production system, for example, and your server is slow, you might want to know where it's spending all its time. And all of these things are really problems because the predominant implementation of Haskell, GHC, is a static compiler. There have been some approach to do like dynamic style optimizations, but in the end it's still a static compiler that nicely generates machine code. At least that's what you would use for production use. For like testing, you can use an interpreter, but it's pretty slow. So my idea is, or obvious idea is to, well, if the problem is static compilation, let's do this stuff at compile time. Which, how hard can it be, right? But we have some success stories actually in the dynamic language department, and I will argue in a moment that Haskell is a dynamic language. Bear with me. So what are the goals? The goals are like, I can imagine two goals when we just focusing on like possible performance improvements from this approach. Number one is, can we maybe get more consistent optimizations where they count? Or can we get, like, have an unoptimized program and then optimize it, but if we, for example, want to see where the program spends its time, then it's nice to be able to relate the optimized code to the source program, while if you have like, if you optimize the program with GHC, it kind of gets vastly distorted in the process. So it often becomes very difficult to map where this low-level optimized program, how that relates to the high-level program. So of course what I did is I implemented a just-in-time compiler for Haskell, or prototype. I am implementing, it's an ongoing process, and I chose to use a trace-based just-in-time compiler. So what does trace-based mean? So when you have your So you have your program with a very simple control flow graph, which eventually calls another function, and then it returns, and then it goes back through the loop. Now, one approach, and that's the approach that GHC does statically, is to in order to optimize this, you basically inline this, and now you have a fairly large control flow graph, and then you try to optimize it as much as possible. Problem is, if you do that at runtime, your optimization probably becomes rather large, and if you optimize at runtime, you also have to pay the compilation cost at runtime. So the idea is to only observe execution paths of the program at runtime, and then compile only those. So what you get then is, you get this, you're only compiling kind of the hot parts of the program, at least that's the hope, and B, you get straight line code, that is, you get locality. And now you see this program here had some control flow edges, and so if we happen to compile this path, but what if this program should take this path instead at runtime? So what we do is we insert a check here that the same condition that causes us to go down here still holds, and then we continue. Otherwise, we fall back, and in this case, we have to execute this part using unoptimized code, so like, for example, an interpreter. And what's happening as a side effect is, so if you call a function, and in Haskell you often have indirect function calls, then this one would specialize on the particular function we called in this particular execution path. So, for example, if you had a generic addition function, but now we applied it to integers, you would get this optimized to integer addition, or any kind of polymorphism kind of have a monomorphic version. And the other thing is, because we're kind of tracing through the execution until we, well, ideally find a loop, inlining happens automatically. So basically anything that is hot becomes part of the trace and then gets optimized as one. So we often can do very non-local optimization. So if we allocate something here and then last use it here, we can remove the whole allocation. And so why do I think this is a good approach? Well, it has been used, for example, to compile languages like Lua, Python, JavaScript, which, well, sometimes we're like moving away from it, but I think that's for another reason. So the idea is it works well for dynamic languages because of this specialization. And Haskell, at runtime, is very dynamic. So when you have, say, even if that thing, well, if it's a list, you would think a list has only two constructors, there's only two cases, not at runtime. At runtime, this thing here could be thunk, so execution could continue in any other part of the program which has type int, and that can be a lot. And the same common problem when trying to do optimizations. You have your program and it has an inner loop, but there's a monad involved. So you have an overloaded bind operation, and yeah, you would really like to get it optimized to your particular use case and not have that indirect function call, because they're really expensive. So I built this thing called LambdaSheen, which so it takes, let's go over here. It uses the GHC API to do all the front level high level optimizations, or not. It was basically independent of the high level optimizations. Then I take that output, compile it into bytecode, and then I start interpreting that bytecode. And during the execution, we have this trace detector that finds hot parts of the code, and those are then recorded and optimized and turned into machine code. And then whenever the interpreter sees a part that it has already seen, as a compiled machine code, it executes directly the compiled version. And you can link them together so that after a while most of the execution is here in the compiled machine code. And one thing that's noteworthy about trace compiler, because we have a straight line code, or just outermost loop, it's actually very efficient to optimize these things, because the compiler is just basically a pipeline of transformations. So how does it work? We have this simple example that kind of demonstrates the typical style in Haskell program, or idiomatic Haskell programs written in. So you have a lazy producer. So this one generates the numbers from this to this, from lower bound to upper bound, but it doesn't generate the whole list. It only returns the next element and then a suspended computation to generate the rest. And then you have a strict consumer that, well, in this case uses an accumulator to consume that data. And the idea is that basically execution jumps between these two. It jumps back and forth between these two. And the idea is by getting them together in the same trace, you can optimize them as a whole and specialize things. And in this case, I'm using like just int types. But if this one, for example, was to use a num dictionary, we would also specialize that onto the observed type. So this program in GHC, slightly older version, with full optimization takes 1.12 seconds. Only the program time excluding garbage collector. And drumroll, the JIT compilation version is slightly slower. And the reason is, actually, if you look at this, so actually my garbage collector for some strange reason is faster, but the allocation rate is the same. So actually GHC managed to do a little bit less allocation. And here's another version of that. This is the extreme case we can get. So the problem that's holding me back on this example is that, we can actually remove all these overheads with some cheese or cleverness.
Okay, we thank the speaker.